Hello and good afternoon, everybody. Welcome to another class of computer-aided engineering using SolidWorks. Today is the first class of SolidWorks simulation, and we are going to go over some of the capability that can be offered by SolidWorks for a method that we call the finite element method, or FEM, and finite element analysis, or FEA. So essentially, what you have learned so far about motion analysis was SolidWorks treating every part of the assembly as a rigid part. And the whole objective of the motion analysis was to have some actuator, some motion in some parts of the assembly, and we were interested into response of other parts, for example rotation of the crankshaft and then a motion of the piston as a response to that actuation. FEA, or finite element analysis, is a totally different perspective of simulation, meaning that it considers that not all of the parts are rigid, like every mechanical object, and they will respond to the forces. And the hand calculation of that often are time consuming. In some of the situation, it's almost impossible without using a computer program to generate the result. We will start from very simple examples so you can see what is the different steps that we have to provide in order to conduct a full productive simulation or analysis using this method. I have brought you up a simple problem, which call it a plate with a hole, and I would like to understand how this part is going to respond to some external forces. For example, consider this is a plate with some geometry and the thickness of 1/2 inch. And let's assume the left part of this plate will be fixed to a fixture, and meaning that this face is not going to move. And the problem asks me that what happens to the normal stress carried out in this part if I apply a 5,000 pound force to this face. And we would like to understand what is the normal stress, what would be the displacement of this part. And let's assume that the material of this part is A36 steel, which is a critical information when we are conducting the simulation. So I have posted some of the shared information that you can as a class material to start that. And let's open a part which is a plate with holes. That should be in a corresponding folder with that. I have provided the sketch of that. If you go to the sketch mode, you will see that I have provided I carried over all the information here except this fillet that we will apply momentarily. If I minimize this, the sketch is fully defined. All the geometry has been defined by the smart dimensions here. So we are ready to make this a extrude boss. So I would like to make it a mid plane, and let's apply 1/2 inch thickness to this part. So you should have the part like this, and there was a fillet on this these two edges for a value of 1/2 inch. So I would start with the fillet command. We do the constant radius command, and I have to select this edge and the other one, and the radius of that is 0.5 inch. So the preview shows it would be a circular fillet like this, which is what we want. This dimension, okay, I just put 0. I do have some static analysis here, which I would delete it from that shared folder so you would see this tab, but I would delete it so you shouldn't see any tab here. This is what I have modeled and examined in this part prior to the class. Okay, so you have your geometry here defined fully, very according to the model that has been provided here. So we can apply the material here, or we can do that later. So let's I can do that later during the analysis. Let's save the file here. So far that we have done. So you should have a simulation tab here. First of all, you have to add it in the require added in option to do that. If you haven't done so, go to the tools and add it in menu, or you can just drop down menu of the setting icon here and go to add it in function. Okay. You go using the tool menu, go all the way here down, and there is an added in. And SolidWorks lists all of the packages that attach to your license. And in order for simulation, make sure that the SolidWorks simulation has been checked in. This check would added this package to the current session. If you make this check, it would add it to the startup, meaning that every time you open SolidWorks, that package is already included. And also SolidWorks estimated that, for example, on my computer, it added 2 extra seconds for every time I start SolidWorks to load up this SolidWorks simulation. When you click on it, if the simulation is not added here, right click on this ribbon and go to the tab and make sure that the simulation is checked in. Then you should have a simulation added here, similar to the other packages that we have so far learned from, like surfaces, sheet metal. This tab is not here by default. Now, if you go to the simulation, there is only one button is been activated, which is a new study, and we are going to start a new simulation case here. So there are multiple scenarios here that you can, and my intention is to show you the introduction of at least some of these simulation case scenarios. We are interested into static analysis, so we will select static, and a name would be appear here. It's called static 1. Feel free to name it anything that you would like, and then click OK. And then underneath, a new tab with the same name that you have picked for this study would be appear, which essentially would be the study for static study. It would be next to the motion study and the other studies that you may have conducted on this part. There are multiple steps that often from top to bottom that you have to apply to this case. The first step is to apply material to your study. So in order to do that, you see, for example, SolidWorks has identified how many parts is he dealing with. It could be, we have started this example by a part, but essentially it could be an assembly. One part has been identified here in order to apply. So the step 1 is to apply the material. Right click on this part, and if there are multiple parts, you can apply all of the material at the same time. This is a simple part, so you're going to go to apply material. A new window would appear here to select your material, which as the problem states, this should be A36 steel. And when you click on it, you will see that this property appears here. The red one are the properties that this particular case of a study would require, meaning that whatever material you would select, it should have a value for this red one, which this database has those value, and we can use it. I select apply and hit close. Okay, so step 1 was allocation of the material, which we already done it. Step 2 is an optional step which is the connections. And essentially the connection is only would be defined if we are conducting a study for an assembly. Since this is a part, we are going to skip to. We should have some other example that we go over this step. So step 2 is optional. Step 3 is fixture. And essentially, and all of these steps that appear here also appear here. So you can use whichever that you are more comfortable with. Is a fixture. So if I right click on it and let's go to fixed geometry, and you see that there are multiple fixture. Whatever that you pick, you can change your options. So I select fixed geometry. So there are multiple standard or the advanced sort of fixtures that you can define. Ours is very simple. It's a fixed geometry. This preview shows what does it mean. Fixed geometry, that one or more faces of your part, you would like to consider it as a fixed geometry. For example, for our problem, it would be this face. But you see that if you select, for example, you see the face is already without any change or displacement. The roller slider, it shows that one axis it would be fixed. It could be like a planar move that you can do that, or it could be a fixed hinge, meaning that one face can rotate around one axis of that. So I'll go with the fixed geometry, and I would select the this face that I want it to be fixed geometry. If you go there, you see that the SolidWorks shows by this one. Essentially, a green color means that no movement across that axis. So if you see that and compare with this coordinate symbol, this face would not have any motion in X, Y, or Z axis, meaning that the part is not gonna move, this face is not gonna move. And that's the only fixed geometry that I have. So when you have selected this part, go ahead and hit this check mark or OK. Okay. So far we have done the material, no connections required, and fixture. Step 4 would be the external loads. And there are multiple external loads that you can apply, like a wide range of the load. And if I'm showing here, which essentially the same thing, you can apply force, torque, pressure, gravity, centrifugal force, bearing load, remote load and mass, or some of these more advanced type of the load. Ours is very simple. I wanted to apply a force on this face for 5,000 pounds. So in order to do that, I have to right click on external load and select force, or you could pick it from this top menu. And then it would say what type of the force is that. Is it force like a linear force, or it is torque? It is a force, and the area of application, and you see that every face that you want to pick, SolidWorks has some preview of the direction of the force that we applied. So I would like to do this force, and here is select. It says, do you want it to be normal to the force, or it would be a select directions, meaning that there is a entity or edge in the part that should define the direction of this force. Mine is very simple. It would be direction to this force, and then I have to specify the unit is a 5,000 pounds, so that would be English. I would select here and then apply 5,000 pounds to this one. And you will see that compared to the problem that I had, the direction of the force is outward. So I have to reverse the direction of the force. And then everything is set, and I would hit OK. Okay, you see that there are two different colors with the arrow of the force has been defined. So that was the step 4. Step 5 is creating a mesh. And what does it mean, a mesh? In finite element analysis, essentially, the idea is when we have a solid object or a surface object, it could be any object that we are going to study, we are going to divide the entire part on assembly to very small pieces along the mesh, and SolidWorks is going to solve the problem considering the boundary conditions, considering the geometry of the part and all the external forces for all of those small pieces across the part. And then essentially that would be the final solution. In order to, when we create the force, you have a better understanding that what is my explanation and reasoning would look like. In order to do the mesh, you are going to right click on the mesh and we are going to click this option, which is a create mesh. And another window would pop up, which essentially would ask, what is the density of mesh? Meaning that how fine or how small those small parts should be. If I select, let's say here is in the half range here, I would show you what does it look like. So if I hit OK, SolidWorks would start creating the mesh. So it would be froze for a second. There you go. So you see that it has created all of these smart mesh, like with the triangle shape across the entire of the body. And the more complicated the geometry or more features would look like, SolidWorks would automatically calculate that which area they have to focus and it have to be finer mesh and which area would be less. So if that's the mesh that has been selected. If I'm going here and go to the create mesh again, now if I drag it to the coarse option, right? And if I hit OK, you will see that it would be like a larger mesh would be created here, meaning that the accuracy of the solution would be a little less than the previous one. And now let's go back to the create mesh again. And here I'm going to bring it all the way to the fine. So if I hit OK, it should typically take more time for SolidWorks to create that. And if you compare the result with the other two options, you see that the mesh are much more finer here, that, you know, essentially the result would be more accurate. I'm going to go back to, I will keep it here somewhere half between the fine mesh and the coarse mesh. I'll put it something like here. So the rule of thumb is the finer the mesh, there would be more accurate result, but the computation time would be more. Essentially, if you have a powerful computer, you can select the fine, but it's always a trade-off between the accuracy of the result and the computation time. For some basic studies, you can, selecting the fine mesh is not really have evident result on the computation time, but we have some of the study that requires iterations of so many calculation scenarios and the frames that essentially if you really select the finest option, the calculation time would be really extended. So be mindful of what mesh setting you would choose for your application. Okay, I have this mesh and we can change the mesh and optimize the result, but for the start this should be good. Okay, so that was a step 5. Go over this step before running the calculation. Assign the material, check the connection, which was optional, assign your fixture, assign your external loads, create a mesh for your setup, and then now we are ready to run this study. If SolidWorks identifies there are some missing step or missing information, it's going to prompt you for that particular information. So if I click run this study or right click and actually this doesn't have here, but yeah, if you click run a study, you will see that a prompt is coming. Essentially it shows you the memory usage and the time. That was fairly simple. And now here is the result that SolidWorks has generated. And let's pause for a second and then identify what has been spit out of this calculation to understand that that process. So first of all, you will see that there are some colors assigned to this part. The part is obviously reshaped, and as a result of that force, essentially it's telling us that by applying that force, the plate would be pulled out. But you will see that the area or the face that we selected as a fixture it's never been shifted for this displacement. So this graph essentially is the deformed result or the displacement result of the calculation. This phase is never changed, but the other parts, like this phase particularly, as a result of this force has been changed. If you wanted to keep the everything, but you don't want it to see deformed, you see that the deformed result has been checked in by default. You just remove it, you toggle it back, you see everything goes back, but essentially there are some displacement here. And there are three different results SolidWorks has presented. The first one is the stress, or the nominal stress, the normal stress, that essentially this is something that problem asks for, normal stress carried out the part. That is the solution. That's the stresses across each part. And for the stress and for any of these, there is a diagram here that essentially would tell us that what is the stress of every part by assigning a different color scale, different color. And this scale shows that what is the value. You will see that they start from some point and all the way go to the red as the stress increase. And if you see, it says 1 Mises. And what is this? Essentially, this is based on a theory that if I want to understand that if there is any area of the part that would reach out to a pressure, to a stress that is a failure, and it would be more than the yield strength. So essentially, as a result, you have to compare the value of the stress, or the 1 Mises stress, with this yield strength. And if there is any value higher than yield stress, that part would be failed, because the 1 Mises stress, or the critical stress, is larger than the yield strength of that particular material. But you will see that even the largest stress that has been calculated for this part is smaller than the yield strength of this material. So the part would not fail. It would be elongated. It would be some displacement across the part, but no more than what we can get out of it, or the part can be failed. So if you just by overall look, you see that the maximum stress that can a part experience because of that external load of these 2 points. And one thing is, for example, if you right click on this one, and you will see if you right click on this scale, you see there is one that is probe. If you pick that, and essentially if you select any point that you would like, you can get a probe of what is that value is, or what is that location essentially is, which is it's assigned, what is that node, which is that number associated with that mesh that has been created. It gives you X and Y Z location and the value of the stress on that point. I'm not interested in that. What I would like to, that would be one tool, but another option is I can actually ask SolidWorks to give me the maximum and minimum of the stress after this analysis. In order to do that, if I'm going to right click on the selected graph, which is a stress, and if I go to definition, there are some options that meanwhile we can do that. For example, here there are multiple options, like if there is a stress or the shear value or anything that I would be interested more. Typically 1 Mises stress is more important feature into that. And actually the unit, I can change it. Here it says Newton per square meter, which I can actually select it based on PSI, because the number was PSI. And if I right click on it, just in between, you will see that the values would be changed to a PSI, which is might be more, it would be easier to compare with this load and the yield strength. And then if I go to the chart option here, I can say show the maximum, which is going to give me right away, or show minimum. and it would be give me that. There are other alternatives or other options that you can pick, like show plot detail, like here it would say what is the name of that. There's a legend that definitely is that bar that is very valuable to see. And then there is something that you can define the maximum and minimum. Unless you have specific reasons, it's always better that let SolidWorks to pick up the maximum and minimum of these values based on the result that he identifies. Then there are other position and formatting that you can try on your time to see how it's gonna impact this data representation. Hit OK. I'm going to go back. So that was the max and minimum that you can do. And one of the cool features of that, if you keep this one and you update this study for the other materials or other external force, this would be a stator and it would be updated automatically. The other result that is very important would be the displacement, which if you double click on it, you will see that now the result would be based on the displacement, which essentially the question is how much this part is going to move because of that load. And it shows you that based on a millimeter, that how much this is moved. But something that you may notice is, number one is that is exactly our expectation. We wanted the left part, which is close to the fixture area, should move less compared to the right part. And you will see that it would progress and it would be increased. And here you have the maximum displacement. That's exactly aligns with our expectation before seeing the solution. And you will see that the maximum displacement here is 0.02 and something millimeter. But here this is definitely far more than what is here. And this is because SolidWorks, the one that you see as a displacement in your monitors, is exaggerated deformed result. They just want to show some exaggeration because if they want to stick to this one, the value would be very minimal to apprehend. But if you wanted to have a true displacement, if you right click on this, go to edit definition, and that was similar to the stress that's shared between all of them, you'll see that the deformed shape actually says automatic, and the scale that they apply is 641, meaning that all of this displacement that's shown here actually is 641 times of the actual displacement. That's why it's exaggerated. But you can, for example, you can apply a user define. You would say, I wanted to even exaggerate more. So if I put like 1200 and apply it, it would be even more exaggerated to show how does it look like. Or if you wanted to put it on true scale, meaning that I wanted to have scale 1, meaning that show the displacement in 1-to-1 relationship between the actual displacement values, you just select that one. And as is expected, this would be very smallest displacement. It would be 0.2 millimeter, very, very small displacement. And next, the other result is the strain, that if you're interested to know about strain values of this calculation. Another result that often, we discussed about that this part is not gonna fail, because if I'm going to the stress and if I compare the calculated stress values of every points of this part, I would see that, for example, the numbers is less than yield strength, and this is the maximum strength that the part can handle before fails. Therefore, this force here is not destructive, and it's because all the max stress and all the stress is less than this one. But we can define it in a better representation, and it's called factor of safety. If I right click on the result, essentially this is all the plots that I can define. And actually, I can give them in a particular equation that I wanted. But one of the very useful result is the factor of safety plots. This is called plot. So, and it says it has a three steps to define the factor of safety. Is look like a wizard. For example, I wanted to apply that factor of safety in all bodies, or selected bodies, which is here is only one. So step 2, move on to next. And I said what multiplication you wanted to see, that is 1 by default. And then here I wanted to see a factor of safety distribution, meaning that I wanted to evaluate that with for all of the parts. And factor of safety essentially is the part that I'm going to divide that value divide by the maximum, the yield strength. And here you will see that the minimum factor of the safety that I can see here is 3 point something that it would be. So I would be in the safety margin of the 3 times of that stress. That is something that might be beneficial, but essentially you will see that the majority of the study, the first two the first two plot is the plot that you would like to always see, that stress and displacement. Those are the big and the major calculation result for the static analysis. And the other thing is you can always change your geometry and recalculation. In order to do that, we are in a static. So let's say I want to change this fillet, instead of 0.5, I wanted to have 0.1 and see what is this result will look like. Is it the maximum is still full false here? It would be changed. In order to do that, let's save first, and essentially SolidWorks would save the result as well as the other setting in a different folder for the static analysis. If I go to model, you will see that. So what I'm trying to say is, if I'm going to here, I'm going to change the fillet feature manager, and instead of 0.5, I wanted to change it to 0.1, which is smaller fillet radius. Hit OK, and you have this part, and save it and go back to static one that you have generated. So here you will see that there are some exclamation mark has been generated. First of all, it would say, the material is okay, fixture is still okay, external load, none of them would change, but the mesh is changed, and that is obvious because the geometry has been changed, and as well as the result. So in order to do that, we can run it, and every time you run the result is going to create the mesh either way. So if I'm going and running the study, it's going to first create the mesh proportional to the geometry changes or other information, and it would generate the result. Is going to generate the result. And now here is something really interesting, and you will see that you will see that now the max value, I'm not really interested to mean, but the max value has been shifted from this part that used to be onto this part. Now this part has the more stress because of this load rather than this one, and the numbers are changed. Now the numbers get closer to the yield, to the yield value. And if I'm going to factor of safety, you will see that now the factor of safety has been dropped to 2 and something, which is essentially, if it's kind of like a comparing of this value to this value, I would say. But that would be the overall result for this part. So this example is finished, and we can move on to other examples for the static analysis.